Good. My name's Tyler Clark. I'm a physician by training, but I have become, in the last several years, much more interested in theoretical biology, specifically ideas surrounding what I call biological computation. So obviously active inference is a natural fit. And today's talk, I'm a little bit, I'm sorry to say, I'm a little bit more disorganized than I anticipated being. I had an edit. I was fine up until yesterday. And then yesterday I decided to try to focus the talk a little bit more narrowly towards the active inference community. What I've got is the slide deck that I've been working on for the last several months. Really, in general, I'm just happy that I get to share with you guys something that's been a big part of my life for the last few months, something I've been thinking about a whole lot. And the idea, since I wasn't able to go with the second slide deck, I'll try to frame it a little bit more verbally. The idea is basically, if you think about Mars levels of computation, algorithm, and implementation, there's a lot of active inference literature on the computational and the algorithmic layers, active inference itself and predictive coding, those sorts of things, but less out there in terms of the implementation layer. How is active inference physically realized in living systems? And to that end, I'm hoping that this talk today provides some type of direction, or at least a foothold, a conceptual foothold for anybody listening. I've done quite a bit of simulation and coding around this idea and found that it works in various different contexts. And I think it would be, I think it explains things like how you actually get the Markov blanket, how that forms in informational and thermodynamic terms. And it does a lot of other cool stuff as well from a relatively simple idea. So with all that said, I guess I'll go ahead and get started. Let me see if I can share my screen or just this part of it. Is that working? There's a lot of layovers on this. All right, that'll work well enough, I think. All right, so I call this conditional symmetry breaking. And I like to start, at least conceptually, I started, and I'm going to try to go fast. I'm going to try to get through all these slides since this is the encyclopedia deck. I tried to start with dissipative systems just in general that are non-adaptive in any sort of way. Hurricanes, tornadoes, all the different examples that are out there. Dissipative systems classically undergo global symmetry breaking in order to create patterns or structure. And global symmetry breaking, while useful for creating some type of organization, is insufficient for creating adaptive organization, memory-laden organization, or hysteretic organization that has any sort of path-dependent memory involved. And so these systems lack an intrinsic mechanism to record or bias future states based on prior conditions. As a result, they're non-adaptive. If the driving conditions change, the self-organizing system collapses. So if a hurricane moves too far north where the waters are colder, and it no longer has that driving energy to maintain the global symmetry breaking, the pattern falls apart, the structure falls apart. Living systems, however, when their environment changes, living systems persist and continue to adapt even though their environment has changed. And so living systems, although dissipative, do something in their symmetry breaking, I believe, that's fundamentally different from what traditional standard Ilya-Prigogine dissipative systems do. This slide, this is more for framing. Basically, systems that efficiently dissipate energy are thermodynamically favored. According to Jeremy England, the free energy principle, I'm sure everybody here is well aware. Living systems minimize variational free energy. But then getting back to the point from earlier, these computational, algorithmic, and implementation layers, conditional symmetry breaking, I think offers a foothold into understanding how these systems can break detailed balance in a way that is accurate to how living systems process information. And so moving forward, conditionality unlocks adaptation because well, in my mind, it's the smallest thing that I can add to a classical dissipative system. This conditionality or conditional response is the smallest thing I can add that would confer adaptability. But as I examined it more, it does a whole lot of other things as well. So the conditionality basically functions as a partial function, I think is the most ideal form in my mind of what this kind of behavior looks like. A partial function has a certain subset of its input domain that it is biased toward, and if the inputs meet whatever the condition is for that subset, then the output of that function, that partial function, is different, qualitatively different than if the inputs were outside of that subdomain. And so this conditionality, even though it's very small and very simple, is I think maybe all you need. I'm not sure, but we'll see. It might be all you need to fully unlock adaptation and allow for the higher algorithmic and computational layers to emerge. But the general idea is that because these conditional steps, these partial functions, are conditioned on a subset of their input domain, whenever they receive inputs that don't meet that condition, the condition doesn't get triggered, the partial function doesn't get triggered. And so there is a discarding of information. And even when the partial function gets triggered, all the residual information, all of the information outside of that subdomain, is essentially lost. And we see this over and over in biology, which I'll get to. But the big takeaway is that when you lose information, you've lost the information needed to reconstruct any prior state. So as you throw away information for each state transition, you are essentially creating a path-dependent process, one that moves forward almost like a computational arrow, like a thermodynamic arrow of time, but for computation in living systems. This creates computational hysteresis. Here are a few biological examples on this slide. So committing steps in glycolysis, anything with a large negative delta G is effectively one way. Cell fate decisions, once differentiated, a cell can't revert to a progenitor state. And then in spatiotemporal summation, inputs that don't sum above whatever the condition is, the triggering threshold, those traces are lost, that information is lost. And that loss of information, that discarding, makes the system then irreversible at that transition. So there's this constant, relentless movement forward in biological computation that occurs because of this discarding of information conditionally at these transition steps. And then also because you're discarding information, and certain information, and retaining other information, the information that was in the subdomain belonging to the partial function, the actual transition history becomes a record of what the system knew or believed about its environment and its internal state at the time that transition was made. And so it functions as a primitive form of memory storage. And so the big takeaway here is that the irreversibility results in a thermodynamic direction. And this thermodynamic direction is where you get asymmetry in biological computation. It's where I believe the Markov blanket forms, because at the Markov blanket, you are explicitly taking some information in and passing it inward autopoietically, and you're discarding other information outside the Markov blanket out back into the environment. And that discarded information, even though we don't have a record of it, is just as important in terms of hysteresis and path dependence. So even though I lean heavily here on irreversibility and these conditional updates, reversible steps, such as those near a delta G of 0, reversible steps are highly important throughout biological computation. The reversible steps, they allow for fine tuning. Obviously, there's no hard lock, there's no commitment in the reversible steps, but if you think about like a biochemical pathway, the reversible steps allow for the reorganization of materials and energy between the steps that are irreversible in a way that is, I don't know what the word is, in a way that is forgiving, that's flexible, that's adaptable in its own right before any type of commitment event occurs. So it's really about a balance between these reversible state transitions and these irreversible state transitions, although I think the irreversible ones end up lending a lot of the things that we contribute, or we attribute, excuse me, to living systems and the way that they process information. So the nice thing about this idea, conditional symmetry breaking, is that it can actually scale. It's not limited to one scale, such as biochemistry or another. In fact, I think on one of the later slides in this deck, a cultural example of conditional symmetry breaking might be the QWERTY keyboard. It's not necessarily the optimal keyboard design, but because it has so much traction and because it has so much historicity in human culture, QWERTY keyboards have stuck around despite their lack of optimal design. And this essentially happens at every layer of biological hierarchy. So even down at the biochemical level, things like rhodopsins, they're conditioned on a part of their inputs and not others. And they're incredibly conserved across animal, archaea, all the different domains. And they may have been one of the first partial functions. I mean, given how conserved they are, they may have been one of the first partial functions to allow these simple proto-life chemical soups to begin responding adaptively to their environment. So the main idea here is that as you get in each layer, from biochemistry to protein, cell signaling, tissue, and beyond, if each layer is embedding a history, then you get this coarse graining that happens as you move upward in the hierarchy. And the coarse graining, even though you can coarse grain the layer below, you can still perform conditional symmetry breaking at the same level. So like I said, spatiotemporal summation is an example that would fit CSB just as much as phosphofructokinase in glycolysis would fit CSB, just as much as a QWERTY keyboard would. So this is not exactly limited to any particular scale. This is something that applies at all biological scales and all levels of organization. And so now we'll get into how this actually becomes linked to Bayesian-like computation, how you can begin to view these many-to-one irreversible commits like posterior formation. And I have apparently a slide in between that one. So we'll just take a break before I get to the next slide. So this is really where abiogenesis is really where I am coming from and thinking about a lot of this. How do you end up with a start with a non-living dissipative system, and what are the smallest things that I can add to turn it into an adaptive living autopoietic system? So persistence in fluctuating environments, historical buildup. We talked about all of these. But one of the interesting things is, for instance, in abiogenesis, the problem of homochirality. Why are all sugars right-handed and proteins or amino acids left-handed? And I might have gotten that reversed. It might be right-handed amino acids and left-handed sugars. But all sugars and all amino acids, respectively, are of the same chirality, and we don't know why in biology. And if you look at conditional symmetry breaking events from a geologic timescale, deep time, it's I think, I'm not going to say obvious, but it's satisfying. It's intellectually satisfying to imagine that these irreversible commits, these conditional symmetry breaking events, were occurring even before the emergence of what we would call life. And so even before we might call a system living, as it was building these layers of environmental response and conditional response, you could get lock-ins. And those lock-ins might lead to a single chirality for amino acids and a different chirality for sugars. And because they get historically locked in, just like a QWERTY keyboard, that lock-in gets preserved down the line, and essentially you become limited in what biological choices you can make with a given organism today, based on the choices, quote unquote, that were made in that proto-life soup, where these irreversible events, these irreversible commits, led to the selection of one type of chirality over another. However, once these systems are able to persist and replicate, natural selection can take over, and we have a pretty good idea of how things go after that. So back to the how conditional symmetry breaking events look like probabilistic posteriors. And I'm trying to keep all of this, I will say, I'm probably talking to people who are far more advanced in their quantitative skills than I am. So I'm trying to keep most of this conceptual, because that is one of the asks here at the end of the talk, is to recruit as many quantitative heavyweights as I can to help formalize these ideas. But basically, you end up with a many-to-one marginalization when you toss out the prior microstates. When you collapse these prior microstates into one, it's the same or similar to how Bayesian inference sums out less relevant paths. You're discarding irrelevant information that doesn't apply to the condition you're trying to meet. And so what happens is that the posteriors end up overriding the priors. And so as this process iterates, you end up with a physical instantiation of prior likelihood posterior, prior likelihood posterior. And as that cycle repeats, you're essentially forming, in physical terms and implementation terms, you're forming the basis of Bayesian inference without using any type of symbolic math. It's implemented in the actual dynamics of the system itself. So explicit probabilities are not needed. And then, of course, and I don't have to get to the three-way connection. Uh, but it's nice in summarizing it. If efficient energy dissipation favors certain structures, these structures act to minimize surprise by maintaining a model of their environment. And CSB is a physical mechanism for this modeling that involves irreversible conditional state transitions. So at this point, this is probably the biggest slide that I would change or tried to. I think it's easily a complement to FEP. I think conditional symmetry breaking is easily a complement, as I said before, because it fulfills the implementation layer where I don't believe there's a lot of literature. There are descriptions in other papers. I think if I recall, and you can correct me, Carl, if I'm misquoting you, but I believe the phrase was, we already know that living systems perform non-equilibrium inference riding on broken detailed balance. And it's that broken detailed balance that I think is really laid out explicitly here. It's conditional, it's irreversible, it creates a history, it creates a computational arrow. And so I think all of these things kind of point to how you can have a very simple idea, just add conditional state transitions to a ordinary dissipative system, and then all of the rest of this falls out. So there's homochirality again. Just to reiterate, slight chiral imbalances became irreversibly amplified and then locked in through computational hysteresis. The same happens actually during development and differentiation. All the lineage commitments execute in a hierarchical cascade. And I've even wondered whether or not this irreversibility, this computational hysteresis, is responsible for aging, not as a byproduct of anything, but the fact that the state transitions are necessarily cumulative. And so this accumulation of information over time specifically describes a biological age. The number of state transitions that a given system has been through, irreversible state transitions that a given system has been through. And I don't know, I'm actually very eager to hear some of the feedback here today on some of these issues. I think teleonomy is another very interesting possibility. Given this thermodynamic arrow to biological computation, is this a possible origin for teleonomy itself? Is goal-directedness or goal-directed behavior merely apparent? And it's really the directionality of biological computation that we're observing when we reference things like teleonomy. I'm not actually sure myself, but these are things that I've been wondering about and things that CSB has given me moments to question. So please feel free. I'd love to hear your feedback on that. Immune repertoire expansions irreversibly restore memory. So if you think about the clonal selection, the clonal expansions that happen in the immune system, B cells, T cells, clonally expanding in response to antigen stimulation, those exposures, the antigens that stimulated them, as well as the clonal expansions that followed, are fully irreversible. And they, if you actually end up, 20, 30, 40 years looking at somebody's immune system over the course of their life, you'll see a specific memory, a specific chain of events of the pathogens that they encountered, the immune responses that followed, and the composition of their immune system, quite literally, written into the history of these clonal expansions. But all in all, the idea is that at all scales, from molecular to the organismal, that conditional irreversibility can explain these, or at least attempt to explain these in a single conceptual framework. And then digging into computational hysteresis a little bit more, because this also affects AI, this affects machine learning. How do we make machine learning algorithms more lifelike, more biologically plausible? And the need for a thermodynamic arrow in biological computation actually led me to wonder whether or not catastrophic forgetting is the result of machine learning algorithms that are simply too reversible. Maybe there's not enough irreversibility, either stepwise or cumulatively. Maybe there's not enough irreversibility to actually store historical information long term. And I actually have an interesting demo to show you, if I can get to it at the end of this slide deck. But yeah, maybe if you can fix the reversibility problem, then catastrophic forgetting is no longer a problem. Oh, and also, if we ever do, if this is correct, if this is biologically plausible, if it takes off, and if we do discover machine learning algorithms that we are able to give this historical path dependence to, just like living systems age and have this cumulative memory of commits, perhaps true AGI, or whatever you want to call it, the next super sentience that's created, if it is biologically plausible, maybe it will experience aging as well, and have unexpected consequences that result. And so the main takeaway here, and like I said, I have some slides here at the end to show you on these points, is that maybe if we take a CSB sort of approach to how we implement machine learning, we can overcome some of the hurdles that we currently experience in that field. So also this affects synthetic biology, because I think that minimal, I'm forgetting their exact name, the phrase that they use for them, autocatalytic networks, I think is what they call it in synthetic biology. But you could very easily drop in irreversible, conditionally irreversible commits into the synthetic biology architecture, the biochemistry that you're playing with in a test tube, to see if these systems adapt more robustly than purely reversible designs. And I think it's a little bit intuitive, actually, that a partially irreversible, I'm not saying every state transition should be irreversible, but at least a partially irreversible system should be able to store more information than a fully reversible one. Because if it were fully reversible, then you wouldn't necessarily be able to ever create any meaningful structure out of it. You wouldn't be able to create the asymmetries that are necessary for structure and organizations. So the whole idea is that by having these commitment layers, by storing this information irreversibly, you're literally etching into the structure of the organism itself its own history. You can do evolutionary reconstructions, so observing path dependence if we reverse certain commits, like Hox genes, for instance. In neuroscience, we can look for direct evidence of these hard locks or commitment events. I still think spatiotemporal summation is a great example of this, but there are many others. And it's also important to note, I am getting towards 16 or 17. It's also important to note that, well, I'll just wait. I'll wait till we get to the other slide. I'll wait for that. but yes, the main thing here is we need free energy models. We need mathematical models. The idea of conditional symmetry breaking, I think, is great in concept, but it needs to be pushed further. It needs formal. It needs to be formalized, and I definitely would appreciate collaborating with anybody on trying to formalize these ideas and turn them into something more mathematically rigorous. So a multi-scale theory of adaptive organization. This applies, again, we can apply CSB to cellular networks. We can consider gene regulatory or regulatory genes as local partial functions that have conditionality and irreversibility. We can think of the same thing at the organism level, the ecosystem level, co-adaptation, path-dependent states of symbiosis or competition, societies. I mentioned QWERTY keyboards earlier. Cultural memes also fit. You can also have things like institutional knowledge, as they say, when you have a group of people or an institution large enough to actually develop its own culture and its own way of doing things and understanding the world. You can actually have CSB implemented at the cultural level as well. So I'm also eager to see to what extent, even though active inference is primarily focused more on the organism level or below, how or to what extent these could be applied, these ideas could be applied to civilizations or human civilization at large scales. Because the more I think about computational hysteresis, conditional irreversibility, and these ideas, the more they become apparent at every scale of organization, biological organization. So conditional irreversible updates unify adaptation from micro to macro levels. And then these, I think we've covered all the main points so far for the concept itself. Conditional symmetry breaking, it's a simple addition to dissipative structures that confers memory and adaptivity. It results in non-bijective irreversible maps because we're discarding information, which then prevents bijectivity and reversibility. You get Bayesian-like emergence, where if you stack these partial updates, you can get directed computation that looks like what living systems do, aging, teleonomy, and this bridges to the FEP because it's a mechanistic substrate for how free energy minimization can actually be physically instantiated in living systems. So it, like I said, in terms of Mars levels of computation, this idea would fit squarely into the implementation layer for active inference. I believe it might have a considerable amount of explanatory power for such a small addition to dissipative systems. Aging, development, homochirality, catastrophic forgetting, and machine learning. It's actually worried me that it apparently has so much explanatory power, but at the same time, the more I think about it, it conceptually seems accurate. It seems right. It's predictive and testable. This is a drop-in. You can drop in CSB in existing machine learning or active inference pipelines and see what benefit it confers. That was actually the script I was trying to work on last night for the other slide deck. Sometimes you see an increase in accuracy, substantial increase in accuracy, depending on the actual implementation. Sometimes you see a reduction in compute per step, so an increase in efficiency. And then other times, really all you're getting out of it are the qualitative benefits, the computational error, the hysteresis, the path dependency. But all of those things are consistent with living systems and how they function. So yeah, this I think together with the current literature on active inference and predictive coding, the algorithmic layer, I think this creates a, uh, a physics to mind framework from the implementation layer all the way up to uh, active inference and the free energy principle. So as I said, formalization is the big one here. This is what I would really hope to achieve, is some type of a collaboration here today that would allow these ideas to be made formal, to be made rigorous, and then of course experimental validation. Um, uh, I really think this could reshape our understanding of a lot of different things under a single conceptual banner, and I think it would really propel active inference forward even further. Um, but yeah, with I don't know how I'm doing on time. 40 minutes. I'll try to these are the original scripts that I wrote, and we can skip what they do exactly, and I can just show you the data. Hopefully, I'll try to be quick about this. But self-organized criticality is something that's always interested me quite a bit, especially the fact that it's so finicky and parameter sensitive, topology sensitive, scale sensitive, and that biological systems seem to implement it no problem. That disparity has always bugged me. So one of the first things I did with this idea is I tried to demonstrate self-organized criticality in a simple 50 by 50 grid. And you see here the 1 over F noise, the power law distribution of event sizes. So avalanches that are small are very frequent. Avalanches that are large are very infrequent. And there's a very particular pattern of the distribution of event sizes there. The fractal dimension is also 1.49, so it fits right in between 1 and 2 dimensions. And then and also the branching ratio is bang on 1 here. And it continues to be. I'll show you some more, and the branching ratio never budges. That was always impressive to me. I never had to do a lot of parameter tuning. It didn't matter what topology I threw it on, how big it was, how big the network was. It always gave me a branching ratio of 1. And then down here in these two plots, there's obvious structure. It's not completely ordered and it's not completely disordered. It's somewhere in between with a reasonable amount of complexity. And the structure that emerges on this lattice, I think, is I mean, the only way I know how to say it is that it's most reminiscent of living systems. If I were to see this kind of structure out in nature somewhere, I wouldn't think it was inanimate. I would think something along the lines of this system is organic, is living somehow. And then I scale it up to GPU. I throw it on the GPU. Again, the branching ratio is bang on 1. I still get similar curves, more structure emerging as I'm now going on a 500 by 500 grid. And you can just see the structures, just like the fractal dimension analysis, it's self-similar. So I can zoom in to a 50 by 50 up here, zoom out to a 500 by 500, and I'll continue to see structure at all scales in between. And these two graphs are showing roughly the same thing. This is just a black and white image of where the most symmetry breaking took place. Then things start to get a little weird. I throw it on a 3D grid, so 500 by 500 by 500. Branching ratio stays the same. Fractal dimension goes up to 2.74 between 2 and 3 dimensions, which is expected. However, the power law distribution of event sizes, and I'm not sure if this is a slicing error or an artifact of how I'm measuring the distribution of event sizes, but the power spectrum and the power law distribution are a little bit off on this one, even if everything else appears to be the same. I did a scaling study. So we've gone from a 50 by 50 up here, all the way down here to a completely different topology, Bayesian, and up to 200,000 nodes. The branching ratio, again, stays bang on 1. The Gini coefficient stays the same throughout all these. And the correlation length increases, as you would expect, as the size of the network increases. Although because it's scale-free, Bayesian, the correlation length doesn't increase as quickly as it would in a lattice with a uniform grid, because you have hubs that make it easier to traverse the network, and so the correlation length grows more slowly. So all I've shown here is basically that I've implemented what I think is robust SOC on multiple topologies at different scales, and that it continues to demonstrate the features of SOC. So at this point, I naively thought, hey, the brain uses SOC, let me throw MNIST at it and see if it can classify handwritten digits, and it failed miserably. So I went back to the drawing board, and basically I implemented a second layer of computational hysteresis. In the design of this first SOC script up here, CSB is implemented to basically tell when a specific cell is going to fire. That cell will look at its own history and its context and decide whether or not it meets some condition, some threshold, and it will fire. And the reset on that scale is very quick. It's quick enough to maintain SOC, and it can't do much else, which is why when I threw MNIST at these simple SOC reservoirs, it did nothing, because there wasn't enough hysteresis there to preserve memory long-term enough to actually allow the reservoir to do anything. However, when I added a integrate and fire potential with an adaptive threshold, that dramatically increased, and that adaptive threshold has a slow cooldown. That increased the computational hysteresis in the system dramatically. So if you look on the left, the blue plot, the original PCA trajectory really never leaves the neighborhood of the origin. It never goes up or down more than 1.5. It goes to the right, I think, a little over 2. But on the right, in the red graph, the red line, with this integrate and fire mechanism added, you can see it starts over here at 0, but then shoots off. This point over here, I think, is 100 units to the right, and then up here it's 30 units up. And so we immediately are covering more space in PCA space. The total path length is 15 for the non-hysteretic model, 260 for the hysteretic model. So once I had this, I tried MNIST again, and this it just shows the scaling. You can actually see an increase in memory capacity as the system scales. There's some other things in here, but I'm trying to be fast. So once I threw MNIST at the hysteretic integrate and fire model, I got excellent clustering. And just on a simple 3 nearest neighbor readout, got 97% accuracy. And this is with no back propagation. This is with no gradient descent. I didn't even explicitly implement predictive coding or active inference or anything else. I was just, I just built a SOC reservoir using CSB at 1 time scale to maintain self-organized criticality. And then once that was set, I implemented another CSB mechanism on a different time scale, a slower time scale. And it was able to remember and classify this classic test to 97% accuracy. This further characterizes what's going on, what that reservoir is actually doing in order to create these kinds of clusters, which we can get into, I guess, in the question. But this is the other big one, sequential learning, which is a no-no in machine learning. Catastrophic forgetting means that when you try sequential learning, the earlier tasks that you trained on will be forgotten by the time you train on the last task. However, in this model, you can see 4 very distinct clusters in PCA space for the 4 separate tasks that the script was trained on. And then when it's asked to retest after training on all 4 tasks and retest, it remembers the first task actually the best, 98.6 on permuted MNIST, the first task that it was trained on. And all the tasks are actually remembered. I think fashion MNIST is the worst, 91.7. But this is I wouldn't call it maybe not a smoking gun, but this is, I think, a powerful demonstration of the computational hysteresis that CSB enables, because you're able to expose the reservoir to sequential tasks that aren't the same task, and it will remember them. It will remember them with pretty high fidelity, in fact. And so just as a demonstration of CSB itself, without even getting into the full benefits of active inference, I think these are powerful demonstrations that CSB on its own is capable of doing quite a lot of heavy lifting. And that's everything that I have. And I'm sorry if I communicated anything unclearly. I'm very eager to hear everybody's feedback at this point.
Thank you, Tyler. That was great. Okay. If anybody has any immediate questions, please feel free to jump in or raise your hand. Andreas?
I think you're, there you go.
Yes, thank you for Tyler for a very rich thought that gives a lot to think about. I think very ambitious and promising. So I first wanted a clarifying question. I understand irreversibility and I understand symmetry breaking, but I couldn't fit together, like, what exactly do you mean by conditional symmetry breaking? Where does the conditionality come in? How does that work? And maybe how does that relate to your examples at the end?
So the conditionality, and maybe I should, the specific condition itself, in whatever state transition you'd like to discuss, the specific condition is likely to be arbitrary. What's important is that the condition sets up an information boundary for what information the state transition is going to take place under, and what information would prevent or never even allow the state transition to take place in the first place. So a good example, I think, of a physically realizable conditionally irreversible state transition would be something like a rhodopsin molecule, where a rhodopsin molecule is only going to respond to input of certain wavelengths of light, and it won't respond to anything else. It won't change conformation for anything else, not for heat, not for salinity, not for pH. It only detects light. And so the condition under which that molecule undergoes a conformation change is the input of a specific wavelength of light. And once that condition's been met, you get a structural change, and that structural change is then able to be used for a variety of other things. Does that make sense? In terms, the condition itself is arbitrary. What matters is that the condition defines information that the system will respond to for that transition, and information that will get discarded for that transition.
Okay, so I think what I was missing was the state transition, that it's a condition for a state transition. And so, and that there's these, and so it assumes that there's these various possible ways of giving input, let's say, and that it can have internal logic or external logic, but it has some kind of logic by which, given a particular input, it will respond in a way that can produce behavior that then is going to lead to irreversibility.
Right, or another example might be like phosphofructokinase in glycolysis. It has a very large negative delta G. And so whenever it's triggered, that is considered irreversible. The Le Chatelier's principle, where if you have two sides of your chemistry equation and you usually draw a double arrow in between, and Le Chatelier's principle says that if you have excess on one side, that it balances out through dynamic equilibrium on both sides. But for a reaction with a high delta, or a large negative delta G, there's essentially only one arrow in that chemical reaction. There's no rebalancing. It's irreversible. And so does that answer your question?
It's helpful, yeah. I mean,
Okay.
I think you're thinking very biologically, and you have a strong background in that, and so that's my weaker background. But so I can kind of imagine, I can kind of understand, like, you have a chemical reaction where you can have if it's near equilibrium, things could, the chemical activity could be going in the one direction and the other direction. But there's going to be situations, like you're saying, where it's just all going down one gradient, I guess, or down one. It's just going down in one direction. So that's how I have to try to.
So yeah, so in glycolysis, if there's excess glucose available, then the irreversible steps essentially make use of the available glucose to process it, right? That's where the irreversibility comes in handy in glycolysis, and the same is true for other.
Well, I think of like sunlight from the sun; it's irreversible, right? Like, it's coming in a one-way direction, but that's more prior to that, like you talked about dissipative systems. So, that's the first assumption, is that you're going to have these one-way types of energy transfers, let's say.
Mm-hmm.
And then this is another layer on top of that, what you're talking about, the conditional aspect of the dissipation.
It's really about, I think it's really about the living system being conditioned in some way on the environment in a way that allows it to persist under environmental fluctuations. That's really what the conditionality confers that run-of-the-mill dissipation can't.
Mm-hmm. And I mean, I have several thoughts, but maybe the first to ask is, I did take a course in automata theory, and they taught us about the Chomsky hierarchy. And so that's by linguist Noam Chomsky back in the 50s. He realized that if you study what kind of languages, if you study different automata and you consider, like, what are they able to figure out, what are the languages they're able to accept, let's say. There's a hierarchy of power, and the lowest being a finite automata, which has no memory. And then there's a push-down automata, which would be like left-hand parentheses, right-hand parentheses. You remember your obligations, let's say. And then you have a linear automata, so it can take something like ABC and make it CAB, which means that, like, B can transfer A across a whole row of C's. So basically, like, if you have a linear bounded automata, it's like a Turing machine that can take a computation somewhere else and use whatever scratch paper it wants, basically. But the strongest full-fledged Turing machine is the only thing that advances it above and beyond that is that it's able to delete a variable, make it disappear, which is irreversible. See, that's the whole power of, like, these, the height of computation is when you're able to just, maybe you go over something, you do some scratch work, you come back with the answer, but, like, you just delete something and no one can figure out, like, and you don't remember, like, how did you do that? How did you get, well, it's over, like, you've gone down that one road. And so it's a little bit of mystery, like, why is that so powerful? But the important point is that it is, and that's where all the power is coming from. So I'm curious if you're familiar with that, or. But
I'm not actually familiar with the specific automata that you mentioned, but what you said about the irreversibility conferring all of these other benefits very much resonates. It's definitely something I've had my mind on the last few months.
And maybe just another point. I like your talk, and you're very, you talk about this ambitious idea of, okay, in a mechanical substrate, how would it develop to minds and things like that? Now, the way I look at things, and this relates to your notion of conditionality, I think I spend a lot of time thinking things theologically, because basically I'm a metaphysicist. So I think like, okay, like, and I think what I'm trying to say is I think you're thinking theologically. It's just, and so there may be benefits like to some to say, okay, this is the mechanical substrate part, but this is just the theology part. So what would be an example of that? So if you think of a God or whoever, whatever would be this initial state where there's nothing else, right? How does it generate anything out of itself? The only thing I ever figured out was that it asks like, am I necessary? Would I be if I was not? So you get like a proof by contradiction. Like if you are, then you are. If you're not, then you still are, because you're God, obviously. But that's not a very convincing argument. So then you have to kind of like go from there and make it more convincing, let's say. But in that type of mindset, you get all these types of ways of thinking about it. Like, let's say God is unbounded, but what if he was bounded? God is. So, but the main ones would be this. One is God is, let's say, like, something's undeniable, but what if it was deniable, right? So that's basically like this proof by contradiction. That's like a one-track thing. How do you transcend a one-track mind? Now, when you say, like, if you had unconditional, like, so God or, truth or whatever is unconditional, it's absolute, let's say. But what if it was conditional, right? So, but conditionality or even unconditionality, I think it's like a two-track mind. You see, so what you're doing, and so when active inference is about an organism and an environment, it's a two-track situation, basically, that you have, you've set up to, and that's why irreversible, like that's the whole compartmentalization, basically saying like, the world is going to do its thing, but I made my choice, maybe something like that, and I made my choice and I can protect my choice. I'm able to protect the choices I make irreversibly from the world, let's say, that's out there. And so then the third one, just to show like the right is like God or whoever could be impartial, but what if God was partial? So God's doing this experiment, just wants to know, but it's yeah, but they need a little help here, right? Or they need a little, we need to make it a little bit more fair, let's say, right? So that would be, I think, a three-track mind. And that's and that resonates like the theory that I work on, like if I were to try to understand, and I am trying to understand active inference, but a three-track mind type of theory where active inference is modeling the gap between the unconscious and the conscious. So the unconscious neural network part of the brain, 100 billion neurons, is really just part of the environment. It's just a mesh that's representing the environment. It's speaking on behalf of the environment. It's what we know. So like there's a mind metaphysically that knows, but there should be a mind that does not know, but asks questions. So unconsciously, we're getting all these answers, this stream of answers, we don't know where they're coming from. But consciously, you rephrase that in terms of variables or slots or whatever, like concepts, things you don't know. So that would be the generative models. And they're trying to, and that's like 100,000 concepts or whatever. So how can you interact that? That's a two-track mind. And then the idea is that there's a third, so you have an answering mind, a questioning mind, but there's an investigating mind that makes sure that those two minds are balanced and then decides in whatever case, well, which one should I go with? The environment or myself, or that's the thing. So that's what's engaging when you speak. That's what's bouncing around inside me.
No, there's definitely a lot about that resonates. I would say the one of the things is I mentioned it, I think, but I didn't get into it very much. Is that I think CSP might actually set up the boundary, the Markov layer boundary, and it's like what you were saying about a two-way street. How you have this exchange of matter and energy with your environment, any living system, right? And at the boundary, essentially, you have a symmetry breaking event where depending on what information is discarded and what information what information the state transition is conditioned upon, you are essentially sending, you're taking in information and then you're sending it two different ways. At that point, you end up with an asymmetry, right? And because part of that asymmetry means discarding that information, and you now don't have it anymore, the state is not reversible. You can't revert to the previous state because the information needed to construct it is gone. And so you're literally creating, and this is not to get to the three-track mind yet, but on the two-track mind part of things, you're creating that Markov boundary, at least in part, I guess, through conditional symmetry breaking and that asymmetry that happens at the boundary, redirecting information flows, one inward, one outward, right? And then everything that happens more internally are going to be these more autopoietic, self-referencing types of information flows. And then of course everything that gets discarded and sent out beyond the boundary is forgotten and lost, and lends to the irreversibility of the state transitions. And then also I think it's interesting to think about, like you said, choice. Like I've made my choice. How really, I mean, if you look at biological systems as composites, especially composites of all of these tiny little state transitions and choices that have to be made, most of which we're unaware of. I find it really interesting to consider the degree. I think you're right. Yes, I've made my choice. My information is here now, and I'm separating it from that information that I'm sending out into the environment. But once that choice has been made, even if I'm not conscious of it, even if it's just a part of my biochemistry and you know, many nested hierarchical layers of which I'm not consciously aware, the same still holds true, that certain information gets discarded, certain information gets kept within, and that helps form a boundary, an asymmetrical boundary that is responsible for the formation of structure, the ongoing formation of structure. So a lot of what you said resonates, actually. I don't know how much, if what I said resonates as much, but oh, your mic is off.
You gave a very rich talk, and I learned a lot. I'm very happy that we're kind of, I think we're connecting. So it's a pleasure. And I should let other people speak, but I have more to add. So
Okay. Thank you.
thank you.
Thank you, Andreas.
Mhm.
Yeah, perhaps I can ask Tyler, could you give some more details to the algorithm you're actually using for those computational simulations?
Yes.
How are you actually processing the input in MNIST, for example?
I think the easiest way to do it, and I didn't include the slides. I can make all of the code. I have it up on GitHub, so I can absolutely, if you just shoot me an email after the talk, I can send you all the code. And I'm way at the beginning. Almost there. So this is the only slide that actually discusses how the script processes information. And this is really just the script to create self-organized criticality in and of itself. So like I said, I started with a 50 by 50 grid, a lattice where each cell could essentially fire. And it fired based on an if-then rule that was determined by a combination of local neighbor activity and internal states.
Okay.
So the memory matrix integrates past activations so that once a cell fires, its history leaves a non-bijective irreversible update. So it has a cooldown, which is much faster than the integrate and fire cooldown down here on the hysteresis script. This integrate and fire is similarly conditional and irreversible, but it has a much longer cooldown. And so the time scale over which it operates is much longer. And I actually think that if I were to get really fancy, I would try to create these nested hierarchies of different timescales in order to tackle different problems or maybe model living organisms or whatever. Because in real living systems, you end up with many nested hierarchies operating at different timescales, from biochemical reactions, which are insanely fast, all the way to lifelong memories and such. So the inhibition that's created through this irreversible update decays over time, like I said, and in the SOC implementations, just trying to create SOC, this inhibition is relatively quick. It's quick enough just to help the system self-organize, and beyond that, it doesn't really remember much. It doesn't stick around long enough. So yeah, to my delight, this script actually worked right out of the gate. When I first ran this the first time, I got essentially this exact output, which if you've ever coded, you know that never happens. You never get anything on your first try, especially not the data that you expected on your first try. But this is pretty much exactly what came out, and it's entirely emergent. There's no hard and fast rules tying it to any type of critical behavior like 1/f noise or fractal dimension or any of that stuff. It's entirely emergent, even to the point where if I throw it on a GPU, if I make it 3D, if I use a different topology like Baire-Bassiel-Baire, or even up to 200,000 nodes without parameter tuning, it's still able to self-organize to critical. And then, the state transitions shift from dissipative pattern formation into an adaptive system that remembers past events. So the self-organized criticality in this script is almost like a very fast treadmill. That's how I think of it. It's remembering just long enough. The CSB in here is remembering just long enough locally to be able to help guide the decision making, if you like, of the state transitions toward a critical result, and it does that fairly robustly at different scales, different topologies. Does that make sense? I mean, it's more of a general idea, but I can absolutely give you the full code.
Just to be precise, so what exactly is each cell accessing in each time step? So it's got access to its neighbors. Are they continuous values? Is this what the different colors are? Each cell takes on a particular value.
So in these plots, the numbers are actually what I call symmetry breaking events. So how many times that conditional irreversibility, that condition was met and triggered. And so you end up with little islands of very high activity. So these are running at almost saturation. Actually, the whole thing is actually running almost at saturation, because even down here, low activity is close to 5,000, which was the total for the run. So they fired almost. I mean, this is actually a fairly uniform plot here. It's just that these values from 4880 to 4980 are given wildly different values, and so you can actually see the structure that emerges. But you can tone this down so that you're not saturated and firing every single cycle. But yes, it's reading the 8 neighbors around it, and it's looking at its own state, and if there are enough neighbors who fire, and if it hasn't fired, the cell hasn't fired in a certain period of time, then it triggers this firing. And then of course all the other cells are doing that simultaneously as well. So
okay, awesome, thank you. Perhaps and then for the learning scenario, how are you going about that? How do you turn this into a learning algorithm?
So that is the hardest thing. I'm still, if I'm fully honest, like when I look at this script and when I think about it, and a lot of it is actually shown here. This is as mechanistic as I can get for this script, because like I said, I didn't even implement at this point active inference or any of that. This was just a CSP demonstration. What it looks like is that so in this bottom left plot, the 2D PCA of the reservoir trajectories, and this is just 2D, but it doesn't matter how many dimensions you use. All of it, when you expose, well, you want the method. So what I do, the MNIST grayscale images are 28 by 28 pixels. And so I created a 28 by 28 reservoir, or some multiple of 28 by 28. So a reservoir just like this, a grid, a square grid, and then onto and I this was after I had made the grid hysteretic with a slower integrate and fire potential. So after it was hysteretic on 2 different time scales, I projected the grayscale pixel values onto the same grid that the reservoir lives on, right?
Yeah.
And I don't remember the exact time steps that I used, but I basically I hold the pixel values on the grid for a certain period of time, 50 steps, 100 steps, whatever, and then let go. And the reservoir will wander off in state space in on a particular trajectory. Yeah. And essentially what I'm looking at here are what these trajectories, when you use k nearest neighbors on where these trajectories end up in state space, simple 3 nearest neighbor gives you 97% accuracy. So somehow, and this is what I mean by it still confuses me, somehow simply by creating an SOC reservoir that's able to remember its inputs for longer than needed and exposing it to data, this kind of clustering, this kind of almost like sorting, like a postal worker maybe, this sorting of digits as they come in, and this is trained on all 60,000 digits in the data set. So I mean, it classifies them robustly. Why though they each get their own special trajectory in state space using this method is still a mystery to me, and it's still something that I'm struggling to understand.
Yeah, I suppose perhaps it would be good to see a trivial case would just be a reservoir which maintains the input through time. So it just copies the input and essentially is a mirror to the input over time. And then you could do nearest neighbors on that. And so it would just be a sort of trivial memory because it doesn't actually do anything. So it would be good to show perhaps how the clusters look differently if you had a sort of trivial memory system which just copies the input and then you map that onto this 2-dimensional space or whatever. What
do you mean by trivial input though?
So if your system just had imprinted on it an MNIST digit and it didn't evolve over time, it just had activity where there were white intensities and no activity where there are 0 intensities, for example. So it just stores the MNIST digit through time without any behavior. Then you could do a nearest neighbors analysis just directly on the input themselves. So the question is how it transforms the inputs beyond what they originally were.
So that overlooks one thing, and that is that this reservoir, so like even though this is fixed, really what this is describing is a dynamic state. This SOC state is a dynamic state. So even though, like for instance, before I did the hysteresis script down here and gave it more path length and PCA space, when I exposed the MNIST data to the reservoir, it was able to maintain criticality. It was able to maintain the branching ratio right at 1, even though I was pushing the system away from that critical state, right? And so when you expose any kind of data, or you input any kind of data into the reservoir, it's almost like pushing somebody till they're off balance. That person then has to recover in order to maintain the critical state. And it's that recovery, I think, that actually lends the specific trajectory that you're looking at. So I'm not sure how you would project data, arbitrary or otherwise, onto one of these SOC reservoirs in a way that wouldn't lead to some type of a specific trajectory, because just for it to maintain its criticality for the exposure duration, it has to remain dynamic, and it has to constantly update in order to resist that shove that you're giving it from one direction, so to speak. So I'm not sure how we would do that, but I play with this stuff all the time. So any ideas like that, throw them my way. I'm more than interested.
Great, thank you. Perhaps we should now hand over to Carl. It's 10 to 4.
Well, unless Andreas wanted to follow up with.
I'll try to connect with Tyler. I'll write you a letter. So then we'll see
Okay.
where we go with that. Okay.
Good, excellent, thank you. That was an extremely rich presentation, and you're clearly on top of your game. Nothing you said, I think, would require any pushback. I think all the intuitions and all the ways of describing the importance of this kind of symmetry breaking and the breaking of detail balance and all of that, I think, is at the heart of certainly biotic self-organization. One could argue all self-organization in real or open systems. I got, whilst you were talking, I was picking up on sort of key themes and key ideas and just identifying a series of papers that spoke to from complementary perspectives, the things that you were saying. My suspicion is you probably read them all, but even if you haven't, I'm going to go through just to feedback in terms of what that idea reminded me of and how it has been foregrounded in other fields or from other perspectives. In your, if you haven't seen them, the papers that I'm going to show, then you will be interested in them, and if you have, you will be pleased that I spotted the parallels. Before we do that, I just want to sort of, I was just looking at the history of our email exchanges, and they do seem to be, I've got this great idea, and I'm trying to find somebody to listen to me. And I haven't got I haven't got a proper job. I've got a great job, but it doesn't allow me the credentials to actually start publishing or exposing or disseminating these ideas. Is that still the situation? So you've got your day job, but you do this for pleasure, and it's difficult for you to find an audience or a set of correspondence with which to take these ideas forward. Is that the basic situation you find yourself in?
I would say largely the only difference is that if I could turn this into my day job, then that would be an even better outcome. But yes, otherwise, yes.
Right. So can you remind, what is your day job?
At the moment, this is it. I'm actually I was scheduled to take step 1 before COVID. COVID happened. They shut down the testing centers. I'm sorry, not step 1, step 2. That's the U.S. medical licensing exam. And when they shut down the testing centers, that it takes months to prepare for those exams. And so it just threw out months of work. And I don't know, I never really got back on that horse. I started getting interested in theory and found this stuff much more enjoyable. And I even do it in my spare time, which is all the time. And so yeah, the main thing is finding anybody who's knowledgeable in my day-to-day life, or knowledgeable enough to really provide a source of feedback. And I'm ashamed to say, I'll admit it, I use ChatGPT because that's really the best option in my world as it is to get feedback on some of these ideas. But yes, it would be excellent to be able to exchange ideas, at a higher level than what my current social network allows.
Right. Okay, that's interesting. So, reading between the lines, then you're not actually practicing as a clinician at the moment.
No,
so you're
I have my degree, but that's all.
I see.
I didn't get my license.
So you're in the luxurious position of designing your own career from this point forward. Basically, that's
If I can pull it off, if I can pull it off.
Right. It's interesting. Yeah, my son was in the same situation, but he was co-opted to go onto the wards and look after COVID patients as a medical student, and they gave him a free pass for the sort of second year of clinical. Just he wasn't able to revise. So the year below and the year above were very very upset about that they managed to get a free pass to the next stage. This is in the UK. And he actually ended up doing medical research in informatics, not quite of this sort, but you know, he found his way forward. Okay, so you know, I did notice that you were looking for collaborations or people to sort of endorse or join the dots with your work. You're not going to find that by unless you, I think, do one of two things. And let me explain what I mean by you're not going to find collaborators for free. I may be wrong with Andreas. Perhaps you and he will become great friends and write, you know, co-authored papers together and become famous. But people like me, we're just too old and overcommitted, and we have our own agenda to follow. That's going to be universally true for anybody you go to. So you have to think about how you're going to forge that career. And it strikes me there are two ways forward. You could get a job that gives you money, a day job that's not actually paying you to do what you love, and then become an independent researcher and approach things like the Active Inference Institute, create a blog page, and leverage ChatGPT in order to get your feedback, and fondly hope that you know, slowly you will develop a status and a standing in the field. That's a little bit risky, and I should just say that people are getting increasingly allergic to anybody, especially independent researchers that uses generative AI. So I receive on average 3 or 4 monographs, theses from people around the world that they have spent 2 or 3 years working out with their large language machine, and there is just not enough bandwidth to even acknowledge receipt of these things. So there has in the past few years been a sea change in the amount of material that's out there, simply because people with no foundational training, you know, want to play this game, and a little bit like yourself, they find themselves without anybody to talk to. It's quite lonely. So the other approach, and what we do is, well, what I do is generally ignore them or point them towards the Active Inference Institute, because there are many levels at which you can find levels of engagement, from very simple things about advice about using Zendo right through to being invited to actually talk about your ideas in a live stream. And that's certainly something you should pursue. And I'm pretty sure I would advise. Have I already given you that advice to go to the Active Inference Institute?
Actually, Daniel Friedman gave me some feedback for this talk, for this very slide.
Oh, wonderful. Right. So you've already got that one. You're not in that class. You clearly know your stuff, and I think could make a substantive contribution scientifically, academically. But that you still face the same kind of problem as being an independent researcher, which means nothing in my world. It just means, oh dear, you know, how are we going to help this person?
Right.
The alternative, of course, is to not become an independent researcher. And if you've got time, you've got to find yourself an MSc and a PhD. I mean, you've got to now find funding and appropriate supervision that enables you to actually say, no, I now have an academic affiliation, and this is my job. This is my chosen career trajectory. I don't know how easy that is going to be in the States. So, you know, if you earnestly look around for PhD opportunities that are aligned with your skill set, you know, I think you would do excellently at interview. You'd overwhelm most potential supervisors in terms of, you know and what you've already done. Is there anything that stopped you doing that so far?
I guess the main thing is identifying. Well, a lot of times, as you said, when I contact primary researchers that are, I guess, relevant enough or appropriate enough choices to be a PhD advisor in my case, for what I want to work on. They're all very much overcommitted, very busy. They have their own schedules, and just getting a foot in the door is one of the hardest things. So.
Right. Yeah. No, I can appreciate. I mean, I can't appreciate that because I'm too old now, so it's a long time since I didn't even do a PhD. But nowadays, you really have to get that foothold in the door. Andreas has just posted something that might be of help. You know, what you could explore is I'm just wondering whether actually a philosophy, a sort of a formally grounded philosophy PhD might be the easiest entree into this. I mean, the kind of things you talk about would immediately suggest to me that you should be looking at the work of people like Mike Levin and Chris Fields, and I know you've been in correspondence with with Chris. And Chris is an independent researcher, but he's now got sufficient stature that he can actually, people do listen to him. So there is a route forward, but I do repeat it, in this age, you're going to be taken much more seriously if you actually have a PhD. But you could. It could be a PhD by publication, or it could be an unfunded, or you could find some way to support yourself, so you don't actually have to get competitive funding or get onto a PhD program, and then approach somebody, I repeat, possibly who just loves the philosophy of this, but also is absolutely intrigued by the maths and the and the ideas that you've been talking about, that will allow you to express your inquiry using the calculus and the formal ideas that you're bringing to the table. So there may be opportunities there which you may not have explored because you were looking for people actually publishing formally in this space, in, say, dynamical systems theory or non-equilibrium steady states or whatever. But there may be philosophers out there who love writing about this in narrative form, who would really value your formal or technical expertise as a supervisee. Then if you could find some kind of way of supporting yourself, that would be, I think, and it doesn't have to be on site. I imagine nowadays you can do this online, so you don't have to move or anything, but you just have to find somebody who's going to accept academic responsibility for you and enable you to do what you want. So I would encourage you to do that. The alternative is just to plug away. Have you published this work? Have you published the MNIST work with the reservoirs?
No, that was actually my hope was that I could get a publication or 2 or 3 after this under my belt, and that maybe that might bolster the case for a PhD position or something. But no, I tried to bring. I think I gave you a talk once before, but it was rushed because it was just a few weeks in preparation. And I had a lot of time with this, and so I really was able to get the ideas straight and how to communicate them. But I tried to bring something to the table this time that I thought would be publishable, or close to it anyway. It probably needs a lot more finer attention, but yeah,
okay, right.
That's what I was aiming at.
Okay, right. So the feedback from this session will be quite important in the sense that I think you're right, and that there will be, if you can write 1 or 2 or possibly 3 preprint like archivable monographs, that will certainly set you up to sell yourself as a prospective PhD candidate. In a way that's sort of comfortable with your lifestyle and other commitments. So I think that's quite a good idea. Please forgive me that I've forgotten. I probably already said these things to you almost identically the last time you do. So I'm getting old now, and I do this twice a week. So sometimes it's difficult to keep on top of all the bright young things, literally, that come to discuss their ideas here. But I think that's a good idea. Yeah, if you can write one or two archive papers and get them out there with the DOI, document identification, that you can then write to somebody like Michael Kirchhoff or Jacob Howie or Majid Beni, something like that, in the sort of in philosophy, but with an eye on important technical formal developments. So look, I've done this. Is this the kind of thing you like, you're interested in? Would you be in a position to supervise me? I think that would be an excellent inroad onto that academic ladder that would then license you to pursue the normal the normal networking and ultimately supervise your own bright young things. That is a good idea. Just again, I'm sure. Forgive me, I've said this before. In so doing, though, you're really going to have to focus on 1 point per paper, and so 3 papers, less than 12,000, ideally 8,000 words on an archive, psych archive, phil archive, bioarchive, whatever, whatever you can get it out there. It's going to be much more impactful and much better for you than a long, diffuse monograph saying, "Oh, I'm really interested in self-organized criticality," but what I'm really interested in is, so focus. 1 point per paper. And it's always more compelling if you can provide both an analytic approach using maths, but also numerical analyses that validate the point. For example, the MDIST digits. That's always a very compelling substance, or lending a substance to an idea or a position or an assertion or proposition or indeed a lemma. But I do repeat, the focus is crucial. 1 point per paper, and keep the paper short. No longer than 8,000 words would be, and I actually make that a rule. If somebody sends me a paper, I'm only going to read the first 8,000 words. If you can't say what you want to say in 8,000 words, it's not worth saying. The alternative is to actually do a review and a monograph, which is much more less an original contribution or novel research, but more of a synthesis. So you can do a longer synthesis should you want to. That would be an alternative, but that would be more sort of historical and just really celebrating the history and the legacy and other people's work and trying to bring it together. You clearly know enough to be able to do that, and with the help of but don't tell anybody, with the help of a large language model, you could do that in a weekend. Although you have to sign, some declaration you didn't use a large language model. So yeah, but I think the first is to identify your 3 favorite points that really sort of landed nicely. And just take your favorite one and then write the paper about that, and then turn to the next one. And usually what you find is that one sort of, if you like, paper builds upon the and you start to build a narrative. But as soon as you can, I would seriously start to think about getting some academic supervision and an affiliation, so that you're on that ladder, and people are not going to have that oh dear response when having to respond to an independent researcher. It's who uses ChatGPT.
I'm sure that sounds awful if that's how I led the discussion, but
oh well, I didn't realize that. No, your presentation and the discussion of your presentation, I would have guessed that you were quite a senior academic stage in your career, but the reality is you're not. So you've got to get there as efficiently as possible. Anyway, let me now just feedback on the science in the fond hope that some of it will be useful. But I repeat, I suspect that you know most about this. There are lots and lots of issues. I think the sort of well, there are so many issues, and hopefully, as I go through the papers briefly, I will be reminded of what the points that I think you should foreground or surface in one of your 3 putative archive papers. But yeah, the first important point is the focus on this conditional symmetry breaking. I think you should break that down into symmetry breaking and conditional symmetry breaking. So first of all, and the reason I say that is that the mathematical formalism that I got from your talk, but also from my understanding of other people and indeed our own work in this space, is that time irreversibility and the kind of symmetry breaking that leads to time irreversibility of the kind that necessarily is apt for describing interesting self-organization, or non-equal, far from equilibrium self-organization, is just a simple statement that the dynamics in question have a solenoidal or a non-dissipative part. And I notice you started with the notion of those dissipative structures, and in the Prigogine kind of sense. But it's actually not the dissipative part of the dynamics that actually endows a system with that breaks a detailed balance. It's a non-dissipative part. So it is sufficient to talk about the kind of symmetry breaking that rests upon time irreversibility, just to say that these are just systems that break detailed balance by having a non-dissipative part to their dynamics at any given scale. And then you have to ask yourself, right, so where does this conditional or contextual symmetry breaking get into the game mathematically? And I think that would be best sold now. Okay, now we're going to take non-dissipative dynamics apt for describing non-equilibrium dynamics into something you repeatedly talked about, sort of multiple levels, different scales, hierarchical settings, separation of temporal scales, and all that good stuff. Take it into the context, which is probably best described in terms of the renormalization group, where you actually have an explicit calculus that allows you to deal with the separation of temporal scales. So, for example, in the MNIST ones, when you had your reservoir computing, you actually had to introduce 2 scales into that, although you may have, under the hood, actually got sufficient variation for a separation of scales within the reservoir. But time and time again, you did frame things in a way which, well, if I was writing this down, I would actually appeal to the renormalization group to write this down, so that now the slow variables at a higher scale, both in space and time, if space exists in this in a background free sense, now contextualize the faster dynamics. Thereby the faster dynamics become conditioned upon the contextual variables that are slowly developing. And that would be, I think, a way of answering Andres's question. What do you mean by conditional symmetry breaking? Well, I mean the kind of symmetry breaking that is a necessary aspect of systems that are open and are far from equilibrium, namely those that are accompanied by breaking of detailed balance, conditioning upon a particular context that is supplied by the scale above in the spirit of the renormalization group. And once I put those two things together, I'm now licensed to talk about not just symmetry breaking. Everybody does symmetry breaking, and you could actually say, in one sense, if there isn't any symmetry breaking, then it's not interesting. And then you start thinking, well, are there any systems that don't have any symmetry breaking? I can't really think of any. I mean, there are these idealized systems in 20th century physics and for closed systems, but all systems show symmetry breaking. And I have to say, also, all systems show self-organized criticality. So understanding self-organized criticality is not terribly, from my perspective, the right kind of angle. There is no system that doesn't show self-organized criticality. So that sort of gives you a different perspective on how you would motivate a paper on self-organized criticality. It is not that, oh, my simulations on the very first instantiation showed self-organized criticality. It would be very surprising if they didn't. Yeah, it is more what aspects, what are the boundary conditions that allowed this to be now a good model of things that exist in the way that you've been describing. But how then can you leverage this natural propensity of all systems that break detailed balance and show self-organized criticality to actually solve the MNIST problem, for example? So one advantage of, if you like, separating the breaking of detailed balance within scale from the multi-scale or scale-free formulation of the kind that Chris Fields often champions, that now allows you to talk about conditional symmetry breaking in the sense that you're now conditioning the faster dynamics on the slower dynamics, both of them showing this hysteresis-like effect. I think allows you also to say, well, there are two ways of looking at self-organized criticality. I can either look at it in terms of the power laws that you're talking about, and and I'll just point to one paper that allows you also to think about any system that can be defined in sense of possessing a Markov blanket can always be read as showing a particular kind of self-organized criticality in terms of critical slowing. That's just a natural consequence of minimizing variational free energy. But there's a deeper sense in which you've also got these power laws getting into play, which is the RG flows associated with the renormalization group operators. So that will allow you to look at self-organized criticality from two perspectives. One, which is the horizontal perspective of within scale breaking of detailed balance, under the free energy principle, for example, where you get a critical slowing for free, that is actually an emergent property of just being, which again speaks this strange inversion. There's nothing magical about self-organized criticality beyond the fact that you exist. If you exist, you have to show self-organized criticality. Why? That's what you need to explain. And that has, to a certain extent, already been explained to a level which I'm comfortable with in the free energy principle literature. What hasn't been explained to the same depth is, I think, something that you would be in a very good position to explain, which is the emergence of RG flows and the scale free, or the scaling laws that are emergent under RG flows as you ascend scales. So that would be the particular focus that you bring to the table with a conditional symmetry breaking. Because what are you conditioning upon? I'm conditioning upon the context established by a higher scale. So now I'm now in a world where I'm not now just dealing with sort of dissipative structures and admixture of conservative and dissipative dynamics. I'm now in the world of thinking, well, what does that mean if I've now got a renormalization group in play? So the same kind of dynamics are now played out at different scales, but each higher scale is now contextualizing the lower scale upon which this symmetry breaking is conditioned. So that would be one, if you like, motivation for just breaking apart, just introducing symmetry breaking and all its guises, and then saying, okay, now let's put this in a scale-free setting with an explicit appeal to top-down and bottom-up causation, or synergetics in terms of circular causality between microscopic and macroscopic. These are different perspectives on the to my mind, a more generic and formal, well, it's not that formal, but a more generic formulation within the context of the renormalization group. The same kinds of laws, the same functional form of the dynamics, or the Hamiltonians, or the Lagrangians, or the free energies are evident at each level, and then you can drill down on the conditioning implicit in either the top-down causation or the bottom-up part of this circular causality. So that was my first big point. The second big point is the strange inversion that I sort of implied in relation to self-organized criticality. Usually in my world, what you're trying to demonstrate is that all of these glorious phenomena, such as self-organized criticality or apparent Bayesian belief updating, are just emergent phenomena from things that exist in some well-defined sense. So you're not trying to you're not trying to work towards a teleonomy in your words. What your job is to say that this teleonomy is as if it is apparent and it is a necessary consequence of things that exist. And from your point of view, the things of interest are those things that break detailed balance, but also do it in the context of the renormalization group. So you're absolutely right. The universe will possess exactly this kind of dynamical structure at any different scale, and also the universe has this scale-free aspect which naturally induces this hierarchical recapitulation of the same kinds of effects at different scales, and therefore providing the opportunity for conditionalization of the dynamics at one level on the level above. One simple way of looking at that, for example, would be the notion of time irreversibility. So you could actually say, well, is this not now a good vehicle or mechanics to explain Bayesian belief updating, in the sense that Bayesian belief updating is not time reversible? Because you're unless you forget, the whole point of doing your updating is that you're accumulating with an arrow of time something, some memories, some knowledge. So the other way of looking at that is any system that shows the kind of breaking of detailed balance you described now naturally and inevitably acquires a teleological, if not teleonomic, explanation or description. I prefer it's less loaded, as doing Bayesian belief updating, and that's the free energy principle. So the free energy principle does not say to survive and to exist you have to model your world or update your beliefs or show the kind of hysteresis that you're talking about, or time irreversibility. What it's saying is, in existing, you must show these to exist. You have to. It will look as if all of these dynamics and their interpretation, teleological interpretations or descriptions, must be present. So you may or may not want to pursue that. It's an interesting thing in philosophy, certainly. What comes first, the existence of it and then all its apparent behaviors, or are all the apparent behaviors necessary for the thing to exist? And the free energy principle certainly takes a slightly more deflationary approach, in the spirit of providing an explanation for everything that's going on. And I think that would be useful for you to consider both angles for each of the phenomena you're trying to describe. So you can either sell your story. If I now leverage reservoir computing and so with a particular focus and commitment to ensuring criticality in the reservoir or liquid state computation, then I can solve problems like recognition of classification problems, as exemplified by the classical MNIST benchmark. Or you could say, simply by existing and in a world in which I am exposed to MNIST digits, it will, just by being there and having the dynamics that enable that, enable my endurance or my non-equilibrium steady state in this kind of world, I will evince those characteristics can be read as the ability to characterize MNIST digits. So there are two complementary ways of selling exactly the same maths, and sometimes it's useful just to sort of expose those two perspectives. Let me, if you just in the interest of time, because I imagine you're getting tired now. Now, where are we? We're on Zoom. We want to share. Oh. Does that mean I've shared?
No, I just stopped sharing my screen, I think.
Oh, right. So how do I? Oh, I see. I see. So I can, in principle, now I can see you. Yeah. Again, please forgive me. I've forgotten that you'd already presented. So it's likely that I'm going to recapitulate some things that I may have already said, but just for completeness, I'll go through it. This starting from the beginning, in terms of what it is to break detailed balance and how that has special relevance for self-organization far from equilibrium of the kind that we need to explain our lived world. I quite like sort of referring back to the work of people like Ping Ao. And indeed, he might be somebody. Well, perhaps. Well, anyway, he would be a potential supervisor, I think, in this instance. So I picked out one of several decades of work where he brings the Helmholtz-Hodge decomposition to the table of any dynamics in order to foreground the importance of the non-dissipative conservative solenoidal divergence-free part of the flow. As the basis of the breaking of detailed balance, and this can be read in many, many different ways in terms of asymmetries in the Jacobian that lead to this not necessarily just hysteresis, but all the different ways in which you can break detailed balance. But he spent quite a long time trying to promote this kind of dynamics as an explanation for evolutionary dynamics, and also at many different scales, both in terms of theoretical biology, but also in terms of sort of an evolutionary perspective on cell biology and cancer and the like. Again, sort of irreversible dynamics you see in the life sciences, although he is at heart a mathematician. So I'm just using this as a sort of iconic, this paper as an example of a large literature that places that establishes an equivalence between the breaking of detailed balance, non-dissipative dynamics, the kind of asymmetries in the dynamics implied by a skew symmetric component to the Jacobian, and non-equilibrium dynamics in open systems. They all entail each other. You have to have this. If you have one, then you have to have all the others, and they're just different ways of articulating the different things, and all very apt to describe the kinds of systems that you're interested in. One thing which, and again, I apologize if I've shown you this before, but your repeated references to this sort of almost ratchet-like idea of self-organization, that you have to have the hysteresis like effect to step up, to basically counter the second law by having these hysteresis-like effects that are then clamped or I can't remember what your the way that you phrased it, but having a one-way traffic, and as exemplified, for example, in kinetics with large delta G, just having a sort of one going once in one direction. I haven't read this for a long time, but I was very taken by this collaboration with a sort of more of a biologist, Kate Jeffrey, I think he's now in Edinburgh, and Carlo Rovelli, the author of Relational Quantum Mechanics. But just sort of looking at self-organization, open systems, and through the lens of this sort of these irreversible processes, building themselves up into increasingly complex systems. So again, if you were writing either one of your shorter 8,000 page archive papers or your inclusive review, I think that this style of thinking, which is very close to the Jeremy England ratchet-like thermodynamic take on self-organization of the kind that you want to describe. I think that would be entirely appropriate. And another view, a completely complementary view on entropy production, I think would be provided by physics. So it'd be nice. This is probably more for the review side. So where would you find the same kind of notion in terms of the physics of measurement? And it may well be that the work of Jaynes is relevant here. So I was just reminded of the way you were setting out the problem, the kinds of things you were talking about. I was just reminded of the way that Jaynes set up his latter attempts to address the nature of or describe dissipative systems or dissipative structures. So I'll just read this out for fun. It seems intuitively reasonable that Gibbs' variation principle determining the conditions of heterogeneous equilibrium, by which I think he means non-equilibrium, far from equilibrium, can be generalized to non-equilibrium conditions. That is, a non-equilibrium steady state should be one that remember, this is just the same as saying a system that breaks detailed balance. That is, a non-equilibrium steady state should be one that makes some kind of generalized entropy production stationary, and even in the presence of irreversible fluxes, the condition for migrational equilibrium should still be the equality of some generalized chemical potentials. And I'm reading your hysteresis as this migrational, wandering, contextual symmetry breaking that's one directional. Even Jaynes in the 1980s was wrestling with these, and interestingly came up with his treatment of a minimum entropy production principle that introduced in this paper the maximum caliber principle, and that's basically a maximum entropy principle but associated with paths. So again, it speaks to your focus on path dependency and the memory. So when you take the maximum entropy principle due to Jaynes and apply it, as he did in this instance, to paths, trajectories, that have come from somewhere and are going somewhere, then you get the maximum caliber principle. But it is an explanation for minimum entropy production of exactly the same sort that was originally formulated to try and describe dissipative structures in the early half of the 20th century. So there's some lovely legacy and stories here. I think you could tease out in a review or just to mention in focusing on one of the point you want to focus on. In this instance, I think it would be just irreversibility and the importance of hysteresis and memory in a pathological formulation from different perspectives before getting onto the conditional side, which I think would require you to move to the renormalization group. I'm sure you've read this. It's probably worthwhile rereading this. And I put this up when you were talking about sort of remembering things by changing things irreversibly, and I was struck by the similarity between that notion and something that Mike Levin and Chris Fields have been talking about more recently, which is stigmergic memories. Changing the environment in some way that in the future will influence you, so that basically the environment remembers something about you that you will recall in the future. Again, invoking a separation of temporal scales to actually to solve the kind of memory problem that you were intimating, but in a particular way, which is physically very easily realizable. That if I change my environment just by leaving my mark, that means that I can that's going to influence and contextualize, and namely possibly provide a particular kind of conditional symmetry breaking when I go back to this part of the world or this part of the environment. Well, I love this paper because it sort of not quite in the spirit that you were, but certainly appealing to some of the notions that you certainly surfaced in your presentation. But it sort of captures a load of predictions and aspects of biotic self-organization, which these people went on to expand upon in their subsequent work. And this does talk about this stigmergic aspect of how things remember and how things develop an apparent cognition. One thing which you might want a nod to, and perhaps even correspond with Chris Fields with, if that's useful, is the problem that you are, or not the problem, but the sort of, the importance of the conditional symmetry breaking and contextualizing that symmetry breaking in a time irreversible way can also, at least conceptually, be linked to the problem of non-locality and contextuality in quantum information theory. So this is outside my comfort zone, but it is a big thing in quantum information theory and quantum mechanics, leading to the kind of problems and paradoxes that the Bell inequality brought to the table in terms of interpreting quantum mechanics. So contextuality is something which is a real issue, philosophically at least, in interpreting quantum mechanics and I repeat, quantum information theory. And it's, I think, just associating the conditional part with the context upon which it is conditioned gives you license now to say, well, in a classical setting or a dynamical setting, we are addressing the contextuality problem that has a non-local aspect, because you've now got the separation of space-time scales. So now, from the higher level, that's say doing the memorizing, because it's just unfolding more slowly and it's accumulated lots of instances at the faster level, there is, and thereby establishes a context. There is a resolution of the context of contextuality in the approaches that you've been talking about, that at least allows you to nod to the equivalent problems in quantum mechanics, which are not framed like that, but certainly exercise people. So I just put that up because that was a more recent bit of work by Chris Fields and Jim Glazebrook that might not be useful. Yeah, so I presume you've read this. It introduces the importance of topological supersymmetry breaking in terms of self-organization, but it does so in a paragraph. Oh, sorry, a section. No, we don't have any more. In a section which preempts or precedes a treatment of the renormalization group. So if you're not familiar with the renormalization group, I suggest you go back to this monograph. It's much simpler than you might imagine, and it's easily derived from the center manifold theorem or Hermann Haken's treatment of non-equilibrium systems, namely synergetics, that itself can be linked to circular causality and the slaving principle, which I think are all apt mathematical frameworks for you to tell a story about conditional symmetry breaking, because it is a symmetry breaking, which is the interesting dynamics at each scale. It's now, how do you contextualize it on the scale below or the scale above? Right. If you took the synergetics perspective, then they talk explicitly about macroscopic and microscopic, very much in the spirit in which you were talking about things. But mathematically, it can be very easily put into the context of the renormalization group. And once you've got that, you've now got the scale-free aspect as well. So synergetics does not have the scale-free aspect. It just talks about two levels. But now, if you think about it in terms of all the way up and all the way down, now you've got the scale-free aspect in play. And then Chris Fields would like to talk to you again. One example of this that doesn't actually exploit the scale-free aspect, but does drill down on the renormalization group for bottom-up and top-down circular causality, of an irreversible sort in an evolutionary context was this brief treatment, which and now I've got a deja vu that I'm sure Daniel should have pointed you towards in his guidance. So this just gives you another perspective on the use of the renormalization group, again in the context of describing self-organization in terms, or interpreted in terms of a solenoidal or non-dissipative a gradient flow on free energy, but with the breaking of detailed bands because of the solenoidal part. Another interesting perspective on that, and this, I think this was related to one of the questions, or perhaps one of the points you made about in the absence of this, if you can't remember, that means you can't do belief updating in the right kind of way. One really simple way of so this is with the teleological perspective, one really simple way of seeing that immediately in the functional form of no, this is it, yes. One really simple way of appreciating the importance of symmetry breaking. So we're not talking about conditional symmetry breaking, we're just symmetry breaking now, in licensing an interpretation of self-organization in terms of self-evidencing, or a variational free energy minimization, or inference that licenses your use of the word memory. I mean, in the absence of inference, there is no need for memory. One way of thinking about this really simply is if you just look at the Helmholtz decomposition of any dynamics, then you can separate the non-dissipative part from the dissipative part, and that now becomes a effectively a Bayesian filter. In its simplest form, it's a Kalman filter. And if we just drill down on the non-dissipative, or the conservative or solenoidal part, which is the thing that breaks the detailed balance, then that is the prediction. So even in the context of the simplest possible process, that shows time irreversibility, that can also be read as an inference process, namely a Kalman filter. So it's not even hierarchical, it's linear, it's just a state estimation machine. You already have at hand the point that in order to accumulate evidence that may or may not be cast in terms of remembering things, you have to have this solenoidal part that breaks the detailed balance, that just is the prediction. To just predict is to effectively imply that your dynamics have this symmetry breaking aspect. So from the point of view of Bayesian updating or belief updating, it is almost trivial to say that everything is irreversible, but you can make that very formal just by saying that even a Kalman filter can be interpreted as having this symmetry breaking solenoidal part that can be read as the prediction part, and then the gradient flow part, the dissipative part of the dynamics, is the correction of the prediction in relation to the prediction error. So that, that's how you sort of decompose the symmetry breaking versus or breaking detailed balance parts from the non-breaking detailed balance parts, or the parts you see in equilibrium systems. So you can find that unpacked in this treatment, and I just put this up because again it speaks to the importance of paths and dynamics, which you emphasized. So you can't do this in the moment. You have to think about the historicity of things in terms of trajectories and in paths. I'll just get rid of this one very quickly. I'm sure I've gone through this before. So the thing about self-organized criticality, I said before that there are two ways you can emphasize the universality of self-organized criticality within scale and between scales, or in a scale free. The within scale one, which would just be speaking to your argument for symmetry breaking, is usually in my world explained in terms of an emergent property of systems that minimize their free energy, or you could describe it in terms of James's maximum entropy principle, where the entropy is the curvature of your Gibbs entropy, and therefore, as you maximize the entropy of in the free energy principle, this would be of the beliefs about the causes of your measurement or your sensation, then the curvature gets less and less. As the curvature gets less and less, the Lyapunov exponents that underwrite critical slowing and the time scaling laws, increasing correlation lengths, now approach zero from below. So this allows you to tell this sort of strange inversion story that just by existing in the sense, or being measurable, either in the sense of the maximum entropy principle or in the sense of the free energy principle, necessarily means your time constants, the dynamics that you will show now become, will all now be characterized in terms of Lyapunov exponents that are approaching zero from below. What will this look like? It will look like self-organized criticality in the sense that you'll have a large spectrum of very slow dynamics. And if I plot this out, I'm going to get a scaling law. So that would be one kind of self-organized criticality that is literally self-organized, because it's just a description of self-organization to a non-equilibrium steady state that is always driven. So this paper actually then goes on to simulate fluctuations in that, so you can get different kinds of self-organized criticality depending upon whether you're being driven by the environment or not in particular kinds of ways, which can be looked at as a kind of memory. Again, to remind you, perception and self-organized criticality. These people, particularly him nowadays, who's in Barcelona, has become increasingly famous for this kind of criticality argument, certainly in neuronal dynamics and self-organization. Good stuff, Deco. We've done that one, good. Oh, right, yeah, we can ignore this. I just liked your word teleonomy. I couldn't remember what it meant. But one of the people I mentioned as potential supervisors, although he might be a bit young, was this Majid Beni, who got me uncharacteristically to co-author one of his philosophy papers on teleonomy and teleology. I've forgotten what these, his analysis. So he's, he might be somebody, or he might know people who might sort of value the opportunity to supervise and learn from somebody like you, if logistics permit. And if you email him, send him my very best wishes. Yeah, so that was carving teleologies joints by Majid Beni, who I think is in Europe somewhere. Good, that's it. That was a stream of consciousness, and I apologize for that, but I hope there were some useful bits. Do you have anything you want to sort of revisit, or?
I think I just need to read up on this, but really, I would like to understand the solenoidal versus the dissipative flows, as one is responsible for breaking detailed balance and the other isn't. I think I'd really like to, because actually the place that I was going after all of this that I've been working on just recently is trying to understand conditional symmetry breaking in the context of autopoiesis and information closure. And what I hear when you say solenoidal is a closed loop where the information stays in the system as a part of the persistence, or whatever you'd like to call it, that makes a living system living. And is that, I mean, is that generally the right idea? Am I anywhere near that?
Yeah, well, there are many different interpretations, and that would certainly be quite an attractive one. I'm just standing back. I mean, the work on self-organization of the kind I'm familiar with, is certainly meant to be a formalization of Machiavelli and Varela's sort of autopoiesis and sort of certain kinds of closure. And the problem with that style of thinking was, although it was beautiful and clearly correct, it was all narrative. There was no maths really. You could get you could actually sort of take it forward or simulate or join the dots with other formulations. So, I think it would be very courteous and the right thing to do to link it to autopoiesis, but don't expect much more than just, say, these formalize and ground the intuitions that you get from that style of thinking in the physics of self-organization. And furthermore, it could have been no other way. There are certain little bits to autopoiesis which we haven't covered, which is the sort of getting the resources to do your self-assembly. But anything that maintains its own Markov blankets or interfaces must be doing that anyway. And it's usually what normally happens is when you start to put it in the context of the renormalization group, you suddenly realize that the context in which I'm doing my self-assembly, my auto construction, my self-assembly, something you get in computational chemistry, which is the same kind of thing that you get in autopoiesis and life sciences. Then you realize again you really need to recourse to the scale-free multiple scales to provide the right context to do your self-assembly. But to come back to your question, yeah, there is certainly an interesting information closure on the solenoidal aspects in the sense that you are circulating on isoprobability contours. So you're not changing the potential of the self-information literally. So self-information technically as the negative log probability of being somewhere in some state space or some event. The whole point of the solenoidal part is it's non-dissipative and conservative. So it circulates on the iso contours. So very simple things like the motion of heavenly bodies or massive bodies, that is just a description when you've only got conservative, sometimes, for example, Lagrangian or Newtonian mechanics with no dissipative part. And then on the other end of the scale, it's all dissipative. And you get to quantum mechanics. So there's no solenoidal part, but it's all random fluctuations. So you can only talk about the probability distributions. Thermodynamics will probably be the same. They don't usually focus on the, and certainly equilibrium thermodynamics ignores the solenoidal part. So it's all the gradient flows and the equilibrium that you get. And you can talk about second laws and the like. What you want to do in the non-equilibrium thermodynamics is actually get that solenoidal part back in again. And that's so you can approach this in many different directions. I recommended Ping-AO's sort of treatment, which I think is sort of relatively new wave. Is sort of started writing about this in the 1990s, and it's now sort of fairly mainstream. But if you just want to look at the maths, you can go back to Helmholtz. So this partition into two orthogonal parts of your flow is really trivial. It's just saying if I take a first order approximation to any differential equation, I've got the rate of change of some variables is equal to the rate of change of the flow with respect to those variables times the current variables. And that's called the Jacobian. And that Jacobian can now be split into symmetric and antisymmetric parts. So I can have half the J minus J transposed plus half J plus J transposed. So you're just arbitrarily partitioning the dynamics of your system into a skew symmetric and a symmetric part. The symmetric part does the dissipative flow. It's got real eigenvalues, so it always goes to some equilibrium. And then the antisymmetric part has no real eigenvalues. They're all imaginary, and they do the solenoidal rotational part, and that just goes on forever. And you put them together, and then you have sort of mixed systems that sort of are always looking as though they're trying to find their equilibrium. Then they get chased away by the solenoidal part, and that's the kind of system that does symmetry breaking, topological symmetry breaking, which you can look at as basically tunneling due to the random fluctuations that allow you to explore the solenoidal trajectories that you would otherwise be pursuing. that separation into the dissipative and the non-dissipative or solenoidal part is due to Helmholtz, and it's called the Helmholtz decomposition, which is why I say you can take it right back to the 19th century, and originally elaborated in terms of hydrodynamics and flows, or flow fields in under conservation. So that's where that original decomposition comes from. So if you just Google the Helmholtz decomposition, you'll see this in 3 dimensions, but you can generalize that to an infinite number of dimensions in a Hilbert space should you want to, or 50 times 50 if you're in your MNIST examples. And then some people call that the Helmholtz-Hodge decomposition, because a younger, I don't know who, and I haven't read the original literature, but somebody actually proved that you could just generalize the Helmholtz decomposition to any arbitrary vector space. But although Ping always tells me off, I refer to it as the Helmholtz decomposition. And he says, no, it's not. It's got all these housekeeping terms, and he's got the and he's absolutely right, technically speaking. But the spirit of this, I think, can be traced right back to Helmholtz. And so you remember water going down your plug hole? It goes down. That's a dissipative part, and the flowing around is a solenoidal part. So most things in our lived world have these 2 parts to them, and it's the admixture that gives you this interesting itinerancy, and it's a solenoidal part that makes things time irreversible. So if I watch you swimming, it is the solenoidal cyclical part of it that allows me to tell you whether you're running the video of you swimming forwards in time or backwards in time. So it's that solenoidal part that does the time irreversibility and breaks the detail balance. If you didn't have that solenoidal part, you'd just have the symmetric dissipative part, and everything would just collapse down to the point equilibrium. And that's classical physics. That's equilibrium physics.
That's a big clarification. I'll have to study up on all of that. The quantitative stuff is where I'm weakest and what I need to learn most about. So this is definitely informative. I appreciate it.
Good. Can I go and have a cigarette now then?
Well, I just wanted to say thank you, Dr. Carl, and if connect with the Active Inference Institute with Daniel Friedman, but also very much invite you to connect with me. My email is at mathforwisdom.com, mathforwisdom@gmail.com. And I also mentioned this fellowship opportunity for people who want to switch careers, which is what you sound like to do AI sentience and things like that. So I put that in the chat. Thank you.
Cool. Thank you.
That's very good. I'm just making sure, because Donna may not have access to the chat, so we'll have to make sure that that's broadcast. The chat is actually also saved in the recording if he doesn't have access to the...
I think I have it.
Good. Of course, we're on Zoom now, aren't we? That's one of them. I should hand back to our glorious chair to reassure us it's all sorted.
Yeah, I'll save the link in the email just in case. Great. Well, thank you, Tyler. Thank you, Carl. Thank you, Andreas. I'll see you all at the next meeting. Perhaps we can finish with a final round of applause for the speaker. Thank you, Tyler.
Thank you. Thank you very much.
Great. Thank you, everybody.
Thank you. Bye-bye.